Okay, good afternoon, everybody. Sorry about the delay today. So any questions about one-sided confidence intervals? Sorry, one population confidence intervals. For mean, variance, different scenarios, Bernoulli population, anything? No questions? How about the general large sample confidence interval? You good? Yep. Do you, for finding what? The confidence interval for variance? The variance is not calculable or the estimator. So which one? Because we have, so if you have like some estimator that don't have closed form solution, that's what you're saying, probably. Thinking you can always approximate that. For example, if this is MLE, and MLE doesn't have closed form solution, when you want to maximize it or minimize it, then you can use numerical method to find an approximation and use that one. That's one possibility to do that. Okay? But that's basically to find numerical values. For derivations, you can use always like parametric to see what would be the derivation. And for numerical values, you can just use approximation. And that could happen, actually. Yeah. Any other questions? Okay. So let's move to next topic, which is, seriously? Okay. Confidence interval for two populations. What if we want to have some confidence interval for the difference of means or difference of basically proportions or ratio of variances? So here are basically the scenarios we are going to discuss. One is the difference of two population means. We want to find a confidence interval for that under two basically conditions. One is we know the values of sigma for both populations. The values of sigma are not known. And we can also talk about like non-normal data when we have large sample. Then we talk about the ratio of variances. Okay? And the last one is the differences for proportions. So let's start with two populations. We have two populations. First one is mu1 and sigma 1. The second one is mu2 and sigma 2. Okay? What we want to do, we know the MLE estimate for this guy, point estimate. What is the MLE estimate for this guy? X bar 1 minus X bar 2. Okay? We also know the distribution of sampling distribution of this point estimator. Okay? We can use the sampling distribution of this point estimator, which is normally distributed. Okay? By the way, we assume that both of them are normally distributed. And we also assume that the random sample, let's see if I use X and Y. Okay, let me use the same notation. So let's call this X bar and Y bar. And we have two random samples, basically, with different sizes. This follows a normal distribution with the difference of mu's and variance is the summation of variances. We had this before. So the only thing that we need to do, use basically this sampling distribution and the property of the standard normal and use the pivot method, okay, to find the confidence interval. This is similar to one population, okay? The only thing that I'm doing, I'm changing two populations to one statistic, which is following a normal distribution. That's it. And as you can see, that's basically normal independent distribution. Very important assumption, X bar and Y bar are independent. So two random samples are independent, okay? Then this is the variance. This is N1 and N2, if you want to write it down. And this is a standard normal. Therefore, I can use the pivot method. And I know that the probability of this quantity between minus Z alpha over 2 and Z alpha over 2 is 1 minus alpha. Then I can basically isolate this mu1 minus mu2 in between. And I can find upper and lower confidence interval this way. Okay? As you can see, X bar and Y bar are the average of the samples, so they are known. Z alpha over 2 from table, sigma 1 and sigma 2, we assume they are known. Okay? N1 and N2 is also sample sizes. So when N is greater than 30, N1 and N2, then we can use for non-normal distributions as well. Any questions? Is it clear? Okay. One example, tensile strength for two different grades of aluminum. So we want to compare basically the difference, actually the mean of two grades of aluminum. So that's why we want to have a confidence interval for this difference. Okay, mu1 minus mu2. We collect two random samples. One is N1 equal to 10. The other one is 12 sample or observations. X bar 1 is given, sigma 1 is given, and then we want to find mu1 minus mu2 confidence interval, 95% actually. So it's easy. X bar 1 is 87.6 and 1 is 10. Sigma 1 is 1. X bar 2 is 74.5 and 2 is 12 and sigma 2 is what? 1.5. Okay? So the upper limit is upper confidence interval, or let's show it with you. X bar minus X bar 1 minus X bar 2 plus Z alpha over 2, and alpha is, this is 1 minus alpha, so your alpha is 0.05, your alpha over 2 is 0.025, and Z of this guy is what? 1.96. So that's the equation I'm going to use. Is it? Oh, yeah. Sorry. Thank you. So it's 0.1. This guy is 0.05. And I think this would be 1.645. Okay. So your X bar 1 is 87.6, so 87.6 minus 74.5. So let's write this down as L and U plus minus. Plus minus 1.645. Sigma 1 is 1. divided by 10. And actually, this should be square root. Sigma 2 is 1.5 squared. Is it the variance or standard deviation? Is the standard deviation divided by N2, which is 12, and the square root of that. Okay, so basically I'm using this equation. If I go back, I'm using this equation. And I can get lower and upper bound for this. I forgot to bring my textbook. Anybody by any chance has the textbook? Nobody's carrying it. It's pretty heavy. Okay. So I don't have the final answer for that. Can anybody use calculator to find this upper and lower limit? I want to do. Oh, you have the PDF of it? I think it's chapter 9 or 10. Maybe I can help you. Did you find chapter 9? Yeah, third edition. That's okay. Chapter 9. Mm-hmm. Oh, that's good. Actually, go up. Okay. No, it's chapter 9. Yep. Yeah. Can you tell me? Yes. Yes. What you added? What? 12.21 and 13. 4998. Okay, that's good. So this is upper and lower. This is lower. This is upper. Okay. So here is the thing. So this is lower limit and upper limit on the confidence of, let's say, 95%. So what inference or what conclusion you can draw basically based on these two numbers? So which one, let's say this is about the tensile strength. Which one is stronger? Mu1 or grade 1 is stronger. Why? Because it's always both L and U are positive. Okay? So what if both of them were negative? Grade 2 is stronger. What if one is positive, the other one is negative? They are the same. So under 95% confidence interval, I cannot there is no difference between the grade 1 and grade 2 in terms of tensile strength. Okay? So these are basically type of inferences and conclusion you can draw based on the confidence interval that you get. Okay? Is it clear? So if both of them are positive, I can say mu1 is greater than mu2. If both of them are negative, I can say mu2 is greater than mu1. Okay? And if one is positive, L is, for example, U is positive and L negative, okay, then I cannot say which one is greater. So I would say they are equal with 95% confidence, or in this example, with 90% confidence. Okay? So how about the choice of sample size? It's very similar to basically one-sided or one population. You remember for one population it was what? Z alpha over 2E squared sigma squared. Okay? Now instead of sigma squared, I have sigma squared 1 plus sigma squared 2. That's it. And as you can see, this is the equation that we have. So if we want to have error, if we want the error to be less than E, then this is the number of samples that we need to observe. And as you can see, it means, observe? Yes, exactly. Yes. So N1 should be N2 equal to N. Or I can say generally N1 and N2 should be greater than N. Okay? Both of them. You can either use equal, or if you want them to be unequal, both of them should be greater than N. That's it. Any questions? Is it clear? Yep.
I assume we're going to kind of take the same approach with like our sampling distributions, where if we're comparing two and we have an unknown variance, it's going to end up being a t distribution.
Yes.
But if we have an n high enough, will it revert back to normal?
Exactly. So as you will see, actually after this, if variances are unknown, then we switch to t. But if your n is large, because the degrees of freedom for that t would be n1 plus n2 minus 1, then n minus 2 actually, and then when n1 plus n2 is very large, then you can do that. You can use z. Anyways, what if we want to have one-sided confidence interval? We just replace alpha over 2 with alpha. The same thing here. So again, for non-normal distribution, we can use this confidence interval when n is greater than 30. Okay, what if variances are unknown? Okay, so we have two normal populations. We don't know the value of sigma 1 and sigma 2 squared. Okay, in this case, we have basically two scenarios or two cases. One is they are unknown, but we assume they are equal. Okay, so sigma 1 squared is equal to sigma 2 squared equal to some number. This should be sigma squared actually. It's a typo here. Okay, so what we can do, we know that based on the sampling distributions, this ratio, which is sample average difference minus the population mean difference, divided by a standard error, follows a t distribution with n1 plus n2 minus 2 degrees of freedom. And this is basically the pool estimator. Okay? Actually, now we can show that why we are using this pool estimator. Previously, we couldn't. So I can show that basically this pool estimator is unbiased. Okay? So what is the expected value of s squared p? Is the expected value of n1 minus 1 is 1 squared, n2 minus 1 is 2 squared, divided by n1 plus n2 minus 2. Okay? So expected value of S2p is n1 minus 1 expected value of S1 squared plus n2 minus 1 expected value of S2 squared divided by n1 plus n2 minus 2. We know that S1 squared is an unbiased estimator for what? Sigma squared or sigma 1 squared. In this case, we have this assumption, sigma 1 squared and sigma 2 squared are equal to sigma squared. Okay? And this is also an unbiased estimator for sigma 2 squared. So I can write it down as n1 minus 1 sigma squared, because these two are the same as sigma, plus n2 minus 1 sigma squared divided by n1 plus n2 minus 2. Okay? And in this case, what I'm going to get, it's basically sigma squared. Yeah. I factorize it, and then I can, that's what I get actually. Okay? So that's why we use this combination for estimating the variance. Okay? Now, if I use t-distribution and use this estimator of variance, then I can find this lower confidence interval and this upper confidence interval. Again, as you said, if n is large, actually this should be if n1 plus n2, let me just fix it right here, right now. Oops. Yes. Here. This should be this guy actually. If your degrees of freedom is greater than 30, then you can use that. You can use Z instead of T. Okay? Any questions? Yeah, go ahead.
Condition I1 plus I2 minus 2 greater than 30 is a little bad in the sense that you can have just one example of N2 but a lot of examples for N1 and it will still be satisfied. Don't you have a limit for each of the...
No, actually, as long as you can estimate that, because put it this way, you are estimating one quantity, which is the variance, and you are pooling all data that you have for estimating that variance. Okay? As long as basically you have n1 plus n2, the pooled variance is enough in terms of like being 30, more than 30. That's enough. Okay? You can have even two observation for one population, and let's say 29 from another population. That's fine. If you have one, definitely it's not good because you cannot estimate any variances using one observation. Okay? Any questions? Okay. One example. In this example, we have two samples. What we want to investigate is two types of cements, and we want to analyze the weight of calcium in a standard cement and cement which is enhanced with lead. What we do, we collect two different samples. The first sample has 10 observations, and the average is 90. So let me write it down here. The first one has this average, and n is 10. For n2, and also S1 is 5, which is a standard deviation, sample standard deviation. Okay, for the second one, I have 15 samples or observations. The average is 87, and S2 is 4. So we want to find, again, a confidence interval. T with n1 plus n2 minus 2 degrees of freedom and alpha over 2. The alpha here says, actually doesn't have any alpha. We assume it's point. Let's assume alpha is 0.05. 1 minus alpha is 95%. Can you double check the book for this example? See what is alpha? 95%. Thank you. So your alpha over 2 is 0.025. And here we have SP 1 over plus S2. So we need to calculate the SP first. S squared P is 1 minus 1 is 1 squared. You already have the equation here. I just write down the numbers. So the first one is 10 minus 1 times 5 squared, which is 25, plus 4 minus 1, I'm sorry, 15 minus 1 times 16 divided by 15 plus 10 minus 2. So what is that number? This is squared of P. Do you have it? Or SP, either. 19.5? 52. Okay. And your SP is square root of this guy. Okay. 4.4. Thank you. So what you do is 90 minus 87 plus minus this guy from table. What is the degrees of freedom? 25 minus 2 is 23. So T of 23 and 0.025.
0.069.
0.069. This is from table. SP is 4.4. 1 over 10 plus 1 over 15. 2.069. And you have upper and lower. Lower is, I'm sorry? 0.72 and lower 6.72. So what is the conclusion here? Is there any difference between these two cements? No. Because lower bound is negative, upper bound is positive. Under 95% confidence. Okay? Yep.
The upper is much more positive than the negative is negative.
So actually that depends on your alpha. Because if you play around with alpha, maybe both of them could be positive. So if you say 95% confidence, that's what you get. If you say 90% confidence, then that could change. Okay? Actually, if you use 90%, could be both of them positive. Because what you do when you have larger alpha, you are tightening your confidence interval. In that case, this could be positive. Then under 90%, you would say, yes, this is better than the other one. Okay? So you can see the difference. So your confidence is different for the first statement and the second statement. So with the second statement, you have 90% confidence. For the first one, you have 90% confidence. Yeah.
We also increase the number of sample.
Yes, if you do that, yes. Then if you increase the sample, then you have a more basically precise confidence interval. Okay? Because always when you do, be careful. Whenever you make a statement or draw a conclusion, there are some errors associated with that. Okay? And this error can be reduced by increasing the sample size. I think next week I'm going to start talking about hypothesis testings. And those hypothesis testings have two errors. One is alpha and the other one is beta. Alpha is very similar to this guy. Beta is something else. And then when you draw a conclusion or making a statement, you can say with what confidence you are making that statement. Any questions? Are we good? Okay. Second case. What if these two variances are unknown? In this case, we are going to use an approximate method. This is not exact method. This is approximate method. Everything up to here is exact, okay? But here is going to be approximate method. And we say it's very similar to the confidence interval for normal distribution when variances are known. You see that? Okay? I'm just replacing sigma 1 squared with this 1 squared and sigma 2 squared with this 2 squared. Okay? I'm not using pooled variance anymore. Why? Because variances are not equal. I cannot pool everything together and then estimate that. Okay? That's why I'm estimating each of them separately. But we know that this basically, it's not going to follow a T distribution, but approximately it follows a T distribution. This is the degrees of freedom that you get. It's a little bit complicated, degrees of freedom, and that's basically the approximation. Okay? S1 squared is the sample variance of first population and second population, and n is the corresponding sample size. Again, when n is large, or n1 plus, not basically, when you're new in this case, you just replace n with nu. When nu is large, then you can replace t with z. Is it clear? Any questions? Okay. So basically, same example. Is the same example? Yes. When variances are not equal. Do we have this example in the book, or it's just made up example? Okay. Yeah. Okay, so what I'm going to do, just simply replace sigma 1. I'm using the other one, and just simply replacing sigma 1 squared with s1 squared and sigma 2 squared with sigma 2 squared. So basically, it's 90 minus 87 plus minus t of 0.025, and nu degrees of freedom. We need to calculate nu. S1 squared, which is 25, divided by sample size, plus S2 squared, 16, divided by sample size, which is 15. Okay? That's the lower and upper limit. For nu, that's the calculation for nu, which is S1 squared divided by n1, S2 squared divided by n2, whole thing is squared, and S1 squared by 1 10 minus 1 plus 16 divided by 10 squared divided by 15 minus 1. Okay. Oh, yes. Thank you. 16 over 15. So you get the degrees of freedom here. Just find the t value, and you calculate your lower bound and upper bound. That's and here result could be different. So you may get both of them positive if you are using this case, because the variance is unknown, so the calculations are different, and it's approximate. Okay. For the case that we want to find the ratio of variances, okay, it's a confidence interval for the ratio of variances, then we use F distribution. This is very important. We know that there is a relationship between f of nu 1 and nu 2 degrees of freedom and f of nu 2 and nu 1 degrees of freedom. We're going to use this relationship for constructing these two one-sided or two-sided confidence interval or two one-sided confidence intervals. So basically, let me derive this one because this is different. Let's say this is F distribution with nu 1 and, or in this case, n1 minus 1 and n2 minus 1 degrees of freedom. So this is the degrees of freedom. I know that S1 squared divided by sigma 1 squared, the whole thing divided by another ratio, this follows an F distribution with these 2 degrees of freedom. Okay? So this is F distribution with these 2 degrees of freedom. Therefore, if this guy is alpha over 2 here, I can say this is F of alpha over 2 with these 2 degrees of freedom. Okay? So if I have alpha over 2 here, what is this guy? F of 1 minus alpha over 2. And 1 minus 1, and then 2 minus 1. Okay? Any questions? No, not now. Not now. So this is just a definition. Okay? I'll switch it later. So in between, what is this probability? 1 minus alpha. So probability of between these two quantities is 1 minus alpha. I continue here. So what I'm going to do, I'm going to have sigma 1 squared sigma divided by sigma 2 squared here, and then basically multiply it by some numbers and reverse it to get that one in between of these two inequalities or bounds. So in this case, I get multiply by this 2 and 2 minus 1 multiplied by this 2 squared, this 1 squared. Yes. Then f of alpha over 2 with the same degrees of freedom multiplied by the same thing. This is 1 minus alpha. Then I just reverse the whole thing. Gives me sigma 1 squared, sigma 2 squared. And this gives me 1 over f alpha over 2 and 1 minus 1, and 2 minus 1. It's 1 squared, it's 2 squared. And this guy gives me okay? This probability again is 1 minus alpha. Any questions so far? Now, I want to use this property here. 1 over f is f of 1 minus alpha, and replace basically the degrees of freedom. So if I want to do that, this would be what? F of 1 minus alpha over 2, and 2 minus 1, and 1 minus 1. Okay? How about this guy? Write it down here. F of alpha over 2, and 2 minus 1, and 1 minus 1. And if you look at the upper bound, you have this. The lower bound, you have this one, which is wrong. Oh yeah, this is lower bound, sorry. That's correct. Because we changed the sign of inequality. This is the lower bound, and this is the upper bound. Yeah. Okay? Does it make sense? Any questions? That's how you get basically the confidence interval. For lower bound, you just replace alpha over 2 with alpha. You good? Okay. So one example. So we have a company manufacturers for jet turbine engines, and we have a process or operation involves grinding a particular surface finish with some component. Two different methods do we have. We have two methods actually, and we want to see which one has a less variability. So what we are going to do, we are going to find the confidence interval for ratio of sigma 1 squared and sigma 2 squared. We have two samples. For the first sample, I have swan equal to 5.1 with N1 equal to 11. And for the second sample, we have 16 observations, and the sample standard deviation is 4.7. So it's easy. The lower bound is this guy, which is 5.1 divided by 4.7 squared times f of, let me see if it is 90%, yes. So 1 minus alpha is 90%. Your alpha over 2 is 0.05. So 0.05 and 2 minus 1, which is 15, and 1 minus 1, which is 10. That's for the lower bound. And for upper bound, it's the same thing. We replace this guy with, oh, actually, this is 1 minus. 95. 1 minus alpha over 2. This guy is alpha over 2, which is 0.05. Degrees of freedom, again, 16 minus 1 and 11 minus 1. That's L and U. Yes.
One slide. Why do you have the upper bound? It goes from alpha over 2 to f of alpha?
So which one? This guy?
Yeah. It has f of alpha instead of f of alpha.
No, actually, this is one-sided.
Okay, gotcha.
Yeah. This is two-sided. If you want to have one-sided, then you replace alpha over 2 with alpha. That's it. Okay. Any other questions? Yeah.
Intuitively, does a single-sided upper or lower bound mean when you're comparing?
I guess case by case different, but you just want to find for the, let's say, upper bound sigma 1 squared divided by sigma 2 squared, you want to see if one is larger than the other. Let me see, how can I put it in words.
Like you only care when it's larger. You don't care if it's.
But it's
lesser.
smaller, yeah. Because if you want to see if it's smaller, I don't. Yeah, yes. If you want to see if like one is larger, then you go with upper, and the other one is smaller, go with the lower, you know. And they are. Yeah, and if you just reverse the whole thing, then you get the confidence interval for the other ratio, okay, which is sigma squared 2 divided by sigma squared 1. Yeah. Okay. Do we have numbers there for these two?
Yeah, it's 0.678 and
0.678.
yeah, and the upper one is 1.887.
1.887. Okay, so now that's very interesting because this is confidence interval for sigma 1 squared divided by sigma 2 squared. What is the conclusion here? Which one is greater? They are the same, okay? So basically you can see 1 belongs to this interval, okay? Therefore the ratio is about 1. So there is no difference between sigma 1 squared and sigma 2 squared. If I had both numbers greater than 1, then I would say I have larger variance for sigma 1 squared. If I had both numbers less than 1, then I would say sigma 2 squared is larger than sigma 1 squared with a confidence of 95%. Any questions? I think we are almost done. We only have one more basically scenario or case for difference of the proportions, which I'm going to talk about on Monday. And then we are going to move on to the basically hypothesis testing. Any questions? Good weekend.